Hi everyone, and welcome to Module 8, Lesson 2. In this lesson, we're going to be doing all of the calculations for solutions. Okay, so the first one we're going to start with is percent by volume. Simply the volume of the solute divided by the volume of the solution multiplied by 100%. So what is the percent of volume of 10 milliliters of acetic acid and 300 milliliters of water? Okay. So my volume of the solute in this case would be the 10 milliliters of the acetic acid. I'm going to divide that by 310 milliliters. Okay, volumes are additive. If I add 10 milliliters to 300 milliliters, it's going to give me 310 milliliters. Hopefully that makes sense to you. Multiply it by 100, and if you follow your sig figs, it gives you 3%. Percent by mass is the mass of the solute divided by the mass of the solution multiplied by 100. What's the mass percent of sodium hydroxide in a solution that's made by dissolving 8 grams of sodium hydroxide in 50 grams of water? So when you dissolve a solid into water, it's typically going to have a density of 1 gram per milliliter. And it's not like the water now weighs more. The solution doesn't weigh more now. So we're going to just do the 50 grams here. Again, multiply by 100, and this will give me 16%. Okay, so it's important to note that volumes are additive, but masses are not. Then we have the mole fraction. It's just the moles of the solute divided by the total moles in the mixture. So what's the mole fraction of 10 grams of glucose if mixed with 50 grams of water? Okay, so we'll take our 10 grams of C6H12O6, turn it into moles. The molar mass is 180.156 grams. That gives me 0.056 moles. Then we have to take our 50 grams of water, turn those into moles as well, and that gives me 2.78 moles. So to determine the mole fraction, sometimes you might see mole fraction as like a fancy X. Mole fraction will be equal to the moles of the solute, which is 0.056, divided by the total number of moles, which is going to be 2.836. You add this and this together for your bottom one. And the answer is just going to be 0.020. Mole fraction does not have units, okay? So no units, don't have to worry about that. Molality. Molality is uncommon, okay? It's uncommon. It is used in something else that I'm going to show you later, but we're not going to do the calculations for it. But molality is represented with a lowercase m. So it's important that we pay attention because there's lots of lowercase m's and things. So we just want to be careful. And that represents the moles of the solute divided by the kilograms of the solvent. So it's asking me what's the molality of the solution with 10 grams of sodium hydroxide and 500 grams of water. Okay, the water is the solvent, the sodium hydroxide is the solute. So I need to take these 10 grams of sodium hydroxide, turn them into moles. 1 mole is 40 grams, and so that will give me 0.25 moles. And I'm going to divide that by 0.500 kilograms, which gives me 0.5. And my unit is going to be that lowercase m. So the concentration, the molality is 0.5, and you would say this molal, M-O-M-A-L, so 0.5 molal. Now, again, not commonly used. Molarity, that's the big one. That's the one that you're going to see a lot. It's moles of solute divided by liters of solution. Okay, so let's do some of these different calculations. What is the molarity of a solution with 10 grams of calcium chloride in 100 milliliters of solution? Okay, so we'll start by taking 10 grams of calcium chloride, turn that into moles, 110.98, which gives me 0.09 moles. Now, a lot of these problems that I'm doing only have 1 or 2 sig figs, which you do want to pay attention to your sig figs. If I'm not It's not my fault. And I'm going to divide that by 0.100 liters, because that's 100 milliliters into liters. And that gives me 0.9. And my unit is going to be a capital M. So that would be referred to as molar. So it's 0.9 molar. And molarity is concentration. Okay, so if you see the word concentration, know it's talking about molarity. This next question is what you would do if you were trying to make a solution. So if you wanted to make a solution, 52.3 milliliters of a 2.8 molar sodium hydroxide solution, you would have to do this in order to determine how much do I measure out. Okay, so we'll just plug in what we know into our molarity equation. 2.8 molar is equal to X moles divided by 0.0523 liters. Again, the bottom has to be liters, the top is moles. I think it's very important that you write the word mole after it, because a lot of you are going to just say, oh, that's grams, and then you're going to be done. But it's not, it's moles. So I multiply both sides by 0.0523, and I will get the number of moles, which is going to be 0.15 moles of NaOH. And then I just say, okay, I know 1 mole, again, 40 grams, which gives me 6 grams of sodium hydroxide. So if I was to make 52.3 milliliters of a 2.8 molar sodium hydroxide solution, I would need to measure out, to weigh out 6 grams. Okay, one last calculation here. How many moles of magnesium chloride are in 60 milliliters of a 0.1 molar solution? So again, 0.1 molar is equal to X moles divided by 0.060 liters. Multiply both sides by 0.06 liters, and you get 0.006 moles of magnesium chloride. And that's it. So that is molarity, concentration, moles over liters. Now, excuse me, when you're all finished with the notes, when we come back, I'm actually going to show you the proper steps to make a solution. So get excited. I don't know. And then we have dilutions. Dilutions are when you make a solution from a more concentrated solution. So you're taking what's referred to as a stock solution, which is the more concentrated. And basically, you're adding water to it in order for it to dilute to a lower concentration. So the formula M1V1 is equal to M2V2. Just keep the more concentrated and the less concentration things up together. So for example, how do I make 1.5 liters of a 0.646 molar hydrochloric acid solution from 2.0 molar solution? So my more concentrated is 2.0 molar. I do not know how much of that I need, but I do know I want to make a 0.646 molar solution. I'm going to change this into milliliters just to make my life easier later on. It does not particularly matter. But when you solve this, that's 484.5 milliliters. So how would I make this solution? I would take 484.5 milliliters of the 2.0 molar HCl and add it to 1,015.5 milliliters of water. Okay. I know that my total solution is going to be 1,500 milliliters. So if 484.5 has to be my stock solution of acid, to dilute it, I'm just adding water, and I'm going to have to add 1,015.5 milliliters. So let's look at the next one. You have 505 milliliters of a 0.125 molar solution. I would dilute it down to 0.1 molar. So keep these things together. 505 milliliters, 0.125 molar, 0.100 molar times X. Now, what does X represent? X, which is 631.25 milliliters, is the total solution amount. So what I need is I have 505 milliliters of my stock solution. And then I need to add 126.25 milliliters of water in order to dilute it down to my total volume of 631.25. And then one more here. How many grams of sulfur are in 562.1 milliliters of a 0.270 molar sodium sulfate? Okay, this is not a dilution one. I don't know why it's here, but we'll do it anyways. So we'll start with the 0.270 molar is equal to X moles divided by 0.5621 liters. X will equal 0.152 moles of the sodium sulfate. Now, what I need, I'm going to erase this stuff here. Now, what I need is to know how many grams of sulfur is in that. Well, then I know for every 1 mole of sodium sulfate, I have 1 mole of just S based on my formula, Na2SO4. So one of the compound gives me 1 sulfur, and then I know that 1 mole of sulfur is 32.1 grams of sulfur, which gives me a final answer of 4.88 grams of sulfur would be in this solution. Okay. I am going to show you how to do a dilution as well at the end of class, so get excited about that as well. Now, let's look at some more problems, and this is going to connect stoichiometry with our solution chemistry. So, 50 milliliters of a 0.1 molar aluminum sulfite reacts with how many moles of barium chloride to make aluminum chloride and barium sulfite? Okay, so I need a balanced equation. So it's going to be Al2SO3 plus barium chloride gives me aluminum chloride and BaSO3, barium sulfite. To balance it, it's a 3, a 2, and a 3. So now that's my stoichiometry, that's my balanced equation. So the only thing that I can get from this is number of moles. If I take the molarity and do X moles divided by 0.050 liters, X will be 0.005 moles of the Al2SO3, the aluminum sulfite. And then how many moles of barium chloride does it take? Well, based on my balanced equation, for every 1 mole of aluminum sulfite, it is 3 moles of barium chloride. And so my answer for this is 0.015 moles of barium chloride. So we can use our concentration equation for molarity to determine moles, and then for moles, we can do a stoichiometry problem. That's a common thing in these solution chemistry stuff. Let's do one more example of this. How many grams of calcium hydroxide is needed to neutralize 25 milliliters of a 0.1 molar hydrochloric acid? Okay, a little background. When you neutralize, the moles of acid will be equal to the moles of base. They completely cancel each other out. They neutralize each other. So I want to figure out how many moles of acid do I have? Let's write out a balanced equation first. We take hydrochloric acid, calcium hydroxide. My products are always water and a salt, which in this case is calcium chloride. And to balance it, we need a 2 here and a 2 here. Okay, so let's take our concentration or volume, 0.100 molar, X moles I'm going to write, if you want to be even more detailed, write what it is that you're talking about. So it's X moles of hydrochloric acid divided by 0.025 liters. X will be 0.0250 moles of HCl. Okay, so now I want to get this to grams of calcium hydroxide. Okay, so for every 2 moles of HCl, I get 1 mole of calcium hydroxide, and then 1 mole of calcium hydroxide is 74.093 grams. And so it will take me 0.0926 grams of calcium hydroxide to neutralize the acid. Okay, so again, with these stoichiometry problems, of course, you need a balanced equation, but with the concentration, you're taking your concentration and volume to determine moles, and from moles, you can do your stoichiometry based on your balanced equation. That's going to come up quite frequently, and in real like chemistry things and like life and stuff, that is super important. Now, the last thing here is colligative properties. I used to do the calculations, but we're not going to do the calculations. We're only going to talk about what colligative properties are. So colligative properties are properties that do not rely upon the particle size, only on the concentration, that is the number of solute particles. Ionic compounds dissociate, so the concentration is based on the number of ions. The two colligative properties we're going to look at: boiling point elevation, freezing point depression. So boiling point elevation, it says the temperature difference between the boiling point of a pure solvent and the boiling point of a solution. You can add ionic compounds in to actually increase the boiling point, okay, of a liquid. And it has to do with, again, the number of solute particles. So if I was to look at salt versus barium chloride, I have to see how many particles will these things break up into. This would be 2, this would be 3. And therefore, the more particles, the more the change. So if I add barium chloride into water, the boiling point will actually be higher than if I added the same amount of sodium chloride. And that's really all we want to keep it at. Freezing point depression is the same thing. I can add an ionic compound in order to lower the freezing point. And if I lower the freezing point, nope, not FR, freezing point. Well, I just write freezing. I'm also going to lower the melting point, which means that it can melt at colder temperatures. And this is what we see in the winter when they put that brine on there. It's a mixture of many different ionic compounds, which gives us many different particles, which actually will lower our melting point even greater. So yeah, so the more particles you see, the more that change will be. And that's really it. We just want to be able to explain those colligative properties in those two things. Basically just saying the more particles you have, the more the change will be. And that is it for this lesson and this module. Like I said in the first notes, it's very short because it's super important stuff, and we would end this with a summative lab assessment, but we just don't have the capacity to do that at this point. Thank you, global pandemic. All right, I'll see you back in class.